Okay, in this video, what we're going to do is wrap up the FBX Loader by getting our drawing code in place, and we need to get the compute transformations in place as well.
Right.
Now, fortunately for us, compute transformations has already been done by Kadara/Alias, which was awfully kind of them.
Yes, very kind.
Anytime you plan on bringing any information in from an FBX file that's going to support animation,
right,
you're going to
skinned
need
information.
That's right. You're going to need the compute transformations. So here we are again in one of those situations of, do we just type out what's already been done, or do we just use it from one of their sample files? And we will use it, but Joel's going to walk through and explain exactly what's going on.
Yep.
So first of all, let's show them where they can find it, what file it's in. So after installing the FBX SDK,
yep, we have our folder here with examples, and we got it from Common before, and we got it from ViewScene before. If you go into ViewScene, I opened up the viewscene.dsp here, and I can just bring this up over here. So we got all this information here. I opened up drawscene.cxx.
Okay.
And right about at, let's see, line 318,
that'll work.
We have a compute link deformation, and that's the deformation that we're looking for right here. Basically, the links are the bones, so we're getting bone deformation here. So what I need to do is simply copy all of this. So simply copy, down. We're only going to need to make slight modifications to this. So I'm just going to need it to there, so copy that information down to the second loop here, not to the entire end of the function. Come back over into my FBX Loader here. Let me just move all the way down to compute transformation. And not that. Control V, thank you. So now we have this entire information pasted in. Now, if you want, you can... we're just going to walk through each of these lines and kind of figure out what's going on here. So first we need to get the link mode, and we'll be using this in a minute. And then what we're doing is we're getting... the link count. We still have the mesh information from here, pmesh.
Okay.
So we're going to be utilizing that to get how many bones we have, the number of vertices we have. Then we're going to create the new set of vertices that we have, the new deformation set of vertices. The link deformation, the matrices, and the link weights, which is our vertice weights. And then we're going to loop through all of these for the additive and just set the identity. If it's additive, that means we're adding deformation onto each link. Then we're going to go through all the link deformations and set it to identity, so there's no transformations to begin with. Okay. And then we're simply going to loop through all of the links. So we're going to loop through, get the link. If this isn't a real link, we're going to just continue to the next one. And then here's kind of the meat of it. We have a reference global init position, reference global current position, global init position, just a bunch of transformations here. And what we're going to do is, if it's additive, again, adding the link deformation onto each other, and it does have an associated model, then we're going to get the transform associated model matrix, so the transformation for that particular model, and that's going to go inside L reference global position. And the L reference global current position, another one, is going to use that get global position that we talked about before, pass it what we want to get the link transformation, and pass it p time and p pose. And then we're going to simply, otherwise, if it's not additive, we're going to get the transformation matrix of the link, passing into the same variable we did here. Notice the difference. This is get transformation associative model matrix, and this one's just transform matrix. The get global current position is going to equal global position, which we calculated above. This is passed to us, remember. And if we go down, then what we do is get the transformation link matrix, the transformation of this particular bone that we're working with, store that into link init global position. Then we get the global position of the link at the current time. That's going to be stored in global current position. And here's where it gets interesting. What we're doing here, I know this is a lot, but it's a lot of transformations, and it's just something that, you have to take into account all these transformations before you get the final result. So you have the link relative init position, which you take the two that we've already discussed, the init position, you get the inverse matrix of that, and you multiply that by the global init position, which we've already got. This is going into the link relative position. Then what we need to do is multiply another set of matrices, so the global current position, which we got a second ago, and the global current position, multiply those two together. And then our final vertex transformation, which takes the relative current position that we just calculated and the link relative init position, which we calculated right here, and multiply them together. Okay. And then what we do is loop through every single vertex, get their current index and weight, and excuse me, simply add these matrices together, add the deformation together. But you'll notice that we're using a matrix scale here. And this is something that is a function that we don't have access to. And we're going to add this into common.h and common.cxx in just a second here. But anyway, we continue here. We add our influence, at this particular influence, at the particular weight, onto the current deformation link.
Okay.
And then we set the link weight to 0. If it's not additive, then we simply add the current link deformation onto the current link deformation L influence, and then we add the weight to the current weight, because the weight is added onto it.
Okay.
And that's all there is to it. That's the entire... I know, there's a whole lot of going on here, a lot of transformations, but this is something that you kind of just have to accept in a way, because there's just all the transformations. Just as long as you understand that the final transformation we get is the transformation that the bone is applying to a set of vertices, then you're set to go.
Okay.
Does that make sense?
Yeah, so to sum it up,
Yep.
compute transformation does what?
Compute transformation is going to calculate the amount of transformation, the transformation necessary to modify each vertex.
There you go. By going through, looking at the animation on all the links or all the skeleton joints,
Yep.
and then using that along with the weights, doing all of our different multiplications to calculate the new position of the vertices.
Exactly.
Okay.
And this is going to be called, again, from the last lesson, for every single frame. We're
Exactly.
baking this
It would have
information
to.
out. So let me go ahead and go over to my view scene here. And again, I said we need this matrix add. One way you can find it easily is just right-click, go to matrix add. And this is in draw scene as well. On the very bottom, we have these three little things: matrix scale, matrix add to diagonal, and matrix add. Just a few functions that allow us to modify matrices. Let me go ahead and copy this, come back over into here, and put that into my common.cxx. So just these three functions. And I'll come over to my common.h and just put their definitions in here so I can access them globally. If I'm going too fast, just let me know. Alright, so we have these three that are calculating that. Our CXX is set. Let's go back to the FBX Loader. And there is one final thing we need to add into our transformation. Remember, this is setting a particular frame. So we need to create a new frame and send that over into our new mesh. So right at the end of our compute transformation, call frame, create a new frame, set his bones to equal the link deformation, and set his weights equal to the link weight. And don't forget to add this into our frame list. Frame. Cool. And we're done. So now we got that. That was the main difficult function. Now let's go up and add the draw code. So let me go all the way up to the draw model. And this one's easy. All we need to do is say if the object hasn't been loaded, obviously we just need to return. So just return. Otherwise we're going to loop through all our objects and draw them out. So objects.size, I++. Get our object, and then draw that particular object. Remember, we have a hierarchy going on here. We can have multiple objects, and draw object is a recursive function that draws all its children as well.
That's right.
So inside of draw object, the first thing we need to do is calculate the last time. Basically, every time draw object gets called, we need to find out when was the last time we called and update our current time to reflect that. So we're going to create a static local variable called last time that holds the last time this object was called. And again, if object equals null, then just go ahead and return. Again, this is a recursive function, so we need a condition to end the recursion, and this is our condition. So let's go ahead and get the mesh. So mesh equals object mesh. So if time does not equal last time, in other words, the time has just changed, let's go ahead and update the frame of our mesh. So this can be easily done. We simply add the amount of difference since the last time we were here. So take our float, so time minus last time. This is in frames. Then we're going to divide by 1,000 to convert it into seconds, because it's currently in milliseconds. Multiply this by the frame rate, and boom, we're done. Because remember, time is passed to us in milliseconds. So by dividing by 1,000, we're converting it over into seconds.
Right.
And then we also want to loop this animation. So if the mesh frame is greater than the mesh's end frame, but we need to make sure it doesn't, basically the frame is absolute, so we need to loop this. So frame minus frame start. And we're just going to set it back to 0, the beginning.
Okay.
And then let's update our last time. So that was the main part here, one of the main parts. Now we need to start drawing our object. So let's go ahead and store our transformation matrix. So let's remember our transformation matrix. So GL model view, push that matrix on. So push matrix.
Let's go and pop it.
And yeah, let's go ahead and pop it so we don't forget. And at the very end here, we simply loop through all our children. So let me just put this code in here as well. So int.
Yeah, again, because it's recursive.
Yep. Time. All right. So now we're drawing all our objects. Now it comes the interesting part. Remember, I said we have all the transformations that we need for our particular thing, but we need to start applying that transformation over, because we know what the current time is. We need to apply the transformation at that frame onto our vertices.
Okay.
So what we're going to do is create an FBX matrix, L link deformation. So a lot like what we did before, and we're going to get the deformation at the current frame. So frames, int, mesh, frame, and we're going to get the bones. This is the deformation that we wanted. And then we're going to get the link weight as well, and this is a double. So L link weight, width, no, weight, there we go. And this is going to be the weights. So we have all the weights. We have the bone deformation that we need. Now we need to loop through all the vertices and apply that information. So let's go through all the vertices. Simply mesh num vertices. And we also need the vectors, the transformation vectors that we have.
Okay.
The vertices that we want to be transformed. So let's create a new list of vectors.
I gotcha.
And we're going to create a list, and it's going to have num vertices. So basically, we're going to copy the transformed vertices into this vector, and once we're done drawing them, delete them. And just to make this even more clear, right after we're done transforming it, we're going to call object mesh draw mesh. And we're going to pass it the transformed verts. Transformed verts. And then after we're done with that, we're simply going to delete all these transformations.
Cool.
And so the job of this loop here is to transform all of these vertices. And now this is really actually very simple. The first off is to get the current vertex, the untransformed vertex. So KFBX vector 4, and we're using the FBX SDK classes here, but when we convert them back over, we're going to convert them back over into our own format. So we have our vertex, and this is going to be getting mesh vertices I.x, and then let me just copy and paste this in here a few times. So .y and .z, and that's good. And the last one's going to be automatically filled in. Our transformed vert at this position, so transformed verts at I, we're going to create a local variable real quick here called transform vector, and this one's going to be the transformed vertex. And this one is going to equal vertex by default, and we're going to modify transformed vertex.
Okay.
And we need the original vertex so that we can have something to base all our transformations off of. So inside of here, what we're going to do is get our link weight as well. So L weight equals L link weight. And then if L weight does not equal 0, so this vertex is influenced, does not equal 0, let's go ahead and transform this vertex. So let's get the matrix, FBX matrix, equals L link deformation at I. Remember, we got the link deformation from the current frame and from the bones array. And we're going to take that matrix and multiply it. So transformed vertex, yeah, thank you, equals matrix.mult t, so multiply the transform, with the vertex. So it's going to transform this vertex with this matrix deformation. And once it's done, it's also going to add the vertex multiplied by 1.0 minus L weight. So the invert of the weight. So it takes the vertex position and says, okay, how much, it's basically weighting the vertex to the current position. So how much does this multiplication, how much is that going to influence the previous one?
Okay.
So if the weight was, say, 0, then 1 minus 0 is going to give you 1. Vertex times vertex is going to give you the vertex, and then the final transform vertex is simply going to give you the original position. So it's not going to transform it at all.
Right.
So finally, once we have this new transformed vertex, let's go ahead and apply this to our transformed verts array. We're going to convert this over into our own vector3 format, and it's going to be of type float. So transformed vertex 0. So the X, Y, and Z. So let me copy and paste this a few times. Believe it or not, we're almost done.
Mm-hmm.
And with that, I think that's everything. So we now have our draw model, our draw object, and our compute transformation.
Very cool. Now we've got most everything in place.
Yep.
What we need to do is run through a debug session, and we're going to do that in the next video.
Right.
Joel, is there anything else you can think that needs to be added?
Well, let me go ahead and really quickly go over into my header file.
Okay.
And yeah, I do have a few extra things I could add into here. Remember in our mesh, we do have some things regarding FBX SDK. I'm going to go ahead and copy and paste this into here as well, just so a person looking at the header file will know that it uses the FBX SDK. And also, we need to include the common.h. And we also need to include the getPosition.h file that we have. Otherwise, and also we're utilizing strings. So let me go ahead and include string.h. And using std string. All right, so yeah, that should wrap it up for this lesson. In the next lesson, we'll be doing the debugging, because surely I made some mistakes along the way.
Okay, awesome. Well, that'll wrap it up for this video. Thanks.